Okay, today we're talking about special right triangles. This is section 7-3 in your text. So let's get started. So we want you to learn to use the properties of two special triangles. We call these the 45-45-90 triangle and the 30-60-90 triangle. Now you'll see these triangles repeated a lot throughout geometry, throughout trigonometry, just because the numbers are convenient, there's nice patterns to them, and so they make for quick problems. But in order for you to really use these problems throughout geometry, and then you'll use them a lot again in trigonometry and possibly even calculus, you have to learn these patterns. And so we're introducing them now, so you have plenty of time to learn them for later. Let's get started with the 45-45-90 triangle. Now, notice with the 45-45-90 triangle, we've got two base angles that are congruent, right? That makes these isosceles triangles. That means our legs are congruent because these base angles are congruent, and our hypotenuse is the longest side, and its opposite, of course, our 90-degree angle. So let's take a look at what happens when we have a triangle like this, and we try to find patterns with those leg lengths. So let's draw one of these. I should have put one of these on the page, but I didn't. So we're going to assume that I can draw. Again, these are not to scale, right? And this is a 45 degrees. And this makes this a 45 degrees as well. Okay, so we know the legs are congruent. So we've got side length, and hypotenuse, right? If we want to find out what that length of that leg is, right, we have to kind of look at what happens when we put that into the Pythagorean theorem. So we have a squared plus b squared equals c squared, right? So that means we have s squared plus s squared equals h squared. Now that means we've got two s squareds equals my h squared, right? So if I want to find out what h is, I can just take the square root of both sides. So that means h is going to equal s times the square root of 2. Okay? Now that's one way to look at things. So whatever my my hypotenuse is just going to equal my side length times the square root of 2. So now we've got everything all in terms of one variable, right? Well, what happens if I look at this and say, now I had 2s squared equals h squared. Now I want to solve, instead of my hypotenuse, I want to solve for my side length. Well, my side squared will equal my hypotenuse squared divided by 2, right? And if I square root both sides, then I get s squared equals h over the square root of 2, which is h, not s squared, just s, h square root of 2 over 2. So, what this means, let me draw a second triangle up here. Is if I want to put everything in terms of my hypotenuse, then my sides are my hypotenuse lengths times the square root of 2 over 2. Okay? So, if you ever forget this, now you know how to derive it as well using our Pythagorean theorem. So let's see what this looks like in actual problems. So, what we really want to do here, oh shoot, I see a typo that did not translate well from my PowerPoint slide. Hold on, let me fix it. Okay, so if my side length is s, to get to my hypotenuse, I just multiply it by square root of 2. Okay, So if my side length is 5, then my hypotenuse is going to equal 5 square root of 2. Okay. Now, what makes things really nifty is if you realize that that other pattern that I mentioned, if I had a hypotenuse of 4, well, let's not use 4. 4 presents other scenarios. Say it's 3. Remember, if I went back from my hypotenuse to my sides, I end up having 3 square root of 2 over 2 for my side lengths. Okay? So both of those ways of determining the sides are appropriate that I mentioned on that previous slide. The only one your book mentions is this one here. Okay, but I wanted you to have both of those triangles so you could see. Now, if you don't have that other triangle and you don't want to memorize it, how do you get from that to that? So, knowing that I have side square root of 2 as my hypotenuse length, if my hypotenuse does not have a square root of 2 in it, I've got to divide by the square root of 2. And so when I take, well, how I did this 3 was, if I take 3 and divide it by the square root of 2, that means I have to multiply it by square root of 2 over square root of 2, which gives me 3 square root of 2 over 2. So, to go from the hypotenuse, or from the leg to the hypotenuse, I multiply by square root of 2. To get from the hypotenuse to the leg, I divide by square root of 2. Okay? So, let's find some missing side lengths. These are all 45 degree 45 90s. Say we've got 3 and 3 here. Well, then our hypotenuse would just be 3 square root of 2. Say we've got 7 here. Then going from 7 back to the side lengths would mean that I would have my side is 7 square root of 2 over 2. Because I'm dividing 7 by the square root of 2, which means I multiply to rationalize that denominator, and so I get 7 square root of 2 over 2, and that's the math behind that. Now it's time for our 30, 60, 90 triangles, and drat if I don't see another typo. Okay, we will fix that. Okay, so 30, 60, 90 have a special relationship, and I'm not going to derive this one for you, but let's just talk about what it is. Okay, so we have a 90-degree angle here, we have a 60-degree angle here, and a 30-degree angle. Notice how my 30-degree angle opens up on my shortest side. How do I tell it's my shortest side? Well, the other sides are multiplied by something greater than 1. Right? So that has to be my shortest side, my S, okay? And to get from my shortest side to my hypotenuse, I just multiply it by 2. To get from my shortest side to my long leg, I multiply by the square root of 3. Now you can see these are, you say, wow, you said this was an easy pattern, but it's kind of crazy. But it's a pattern, and it's a pattern that doesn't happen in other triangles, okay? So let's see what this is going to look like in problems. So let's find some missing side lengths. Remember, this is my 60, this is my 30. If I have a side of 2 here, then I know this side is going to be 4, and this side will be 2 square root of 3. If I have this side as if I have the hypotenuse as, let's give it something even, we'll give it a 10. And that will be 5, and that will be 5, and this will be 5 square root of 3. Okay? The difficult problems come, and let's erase some of these and do a few more examples with these triangles. The difficult problems come when you get just given this long leg. Okay, say this long leg is 4. To get from the long leg to the short leg, I have to divide by square root of 3. So this is going to be 4 divided by the square root of 3, which means I have to, in order to rationalize that denominator, I have to multiply by the square root of 3 over itself, which gives me 4 square root of 3 over 3 as my short leg. And to get from my short leg to my hypotenuse, I multiply it by 2, so this becomes 8 square root of 3 over 3. So now we still have that relationship where the short leg is half the hypotenuse. And if we take our short leg and we multiply it by square root of 3, we will get 4. How do we verify that? Well, let's do the math. 4 square root of 3 over 3 times the square root of 3 is just going to be 4 times 3 divided by 3, which is just 4. So we have now verified that every which way we can. So what have we learned? We've learned patterns for side lengths on both 45, 45, 90 and 30, 60, 90 triangles. We've learned how to get from various legs lengths to any other leg length. So given one leg length of any of these two triangles, we can get to the other leg lengths. Okay? So the beauty of it is these patterns allow us to do much more with much less data given. So we'll practice that and have lots of fun with it. See you guys in class.